Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so this is about a project which is founded by LACCIR, and these are the main goals of this project. The first one is discovering meaningful learning scenarios where the pedagogical information loop applies. What do I mean with this information loop? Well, the information loop, pedagogical information loop, may start in the classroom where the teacher tells something to the students, gives some material, then the students take this material and go out with mobile devices, maybe collecting data, discovering things, and they then process this material at home in their desktop computer to prepare presentation and go back to the classroom where they present what they found, and maybe the discussion may trigger another loop of this pedagogical information. The second one is, of course, develop the necessary learning support, the tools for supporting these learning scenarios, and implement a coherent and unified HCI model across these various platforms and scenarios. We have here the classroom with e-boards and desktop computing, maybe mobile devices. Here, mobile collaborative computing. Here, the desktop computing scenario, and back to the classroom. But today I also want to tell you how did I came to this subject, the story of, about how did I came to this subject. And this is a story about trying to use technology, computer technology, which is available to support learning scenarios. And of course, to tell you about the mistakes I made and what did I learn about them, okay? For this, we have to go back very many years ago when I started my PhD at IPSI GMD Institute in Darmstadt, where I came to make my PhD in the year '93, and they received one of the two first electronic boards that were released to the market, and they were two groups that worked with these mobile devices. The one was led by Norbert Streit, and he founded his Dolphin group, and maybe the most important project was this Ambiente with the disappearing computer. And the other, which was my group, was led by Ulrich Hoppe, which was the COSOFT group, and was about the computer integrated classroom. COSOFT stands for computer support for face-to-face teaching. Of course, the people in learning science will say teaching is a bad word. You have to centrate in the learner, but teacher fits better for COSOFT than an L, okay? So then Professor Hoppe and I moved to Duisburg, where we founded the Collide research group, and we developed a set of interesting applications, trying to enrich the interaction in the classroom, the teacher-teacher interaction, and also the student-student interaction. Here you see two of these applications, one for supporting argumentation, and the other for teaching functions and their derivatives. So we also saw very, very interesting things happening in the classroom. For example, merging two medias. And one of the most interesting projects we did was the NIMIS classroom. And this was about computers supporting writing and reading learning for the first grade students in the classroom. This was about embedded technology in the classroom. In fact, you wouldn't see any computer any computer in the classroom. They were all hidden. You will see just screens, touch-sensitive screens. And we used one of the things we developed was this reading through writing methodology, which is about children having to drag the letters from this palette you see, and forming the words that the computer will read for you. And by this methodology, they should learn how to write well. This is a methodology developed by a Swiss teacher, which is very common in Germany and Swiss and Austria, of course, and will fit for languages like German and Spanish and languages which have a fixed rules about how they should be written, not for English, not for French. Okay? And there were many challenges, because how do you make a file manager for people who cannot read? Or a login process, because we wanted the students also to resume their work after a day or after 2 days and so on. So that was the very interesting challenges, also HCI challenges. Back in Chile, this was taken just 3 days ago to illustrate this. But more or less, I tried to teach Java programming with this new device, okay? And I thought, well, I don't need to develop a new software for this. We have already what we need: a PowerPoint for the presentation, a text editor for writing the program, system console, of course, and file system browser. Or we can just take the integrated development environment and have these things here. But you see that these applications are meant for desktop computing, not for the electronic boards. When you are in the classroom with an electronic board, then you have more than one user for your software, and it's a totally different situation. And I will show some of the answers to a questionnaire after the semester. Okay. The teachers simply spend too much time trying to show us things. We get easily distracted in class. I started to take some books with me and began to read them there. Finally, I quit attending classes. This was very embarrassing to me. Yeah? I used to be a good teacher, and I tried to use the new technology, and it didn't work. Really, it was... I tried to make an interpretation. What did wrong? Well, I was doing too many things. What does it take too much time to move from a program to another? And we we named this problem the focus of attention problem, or students' distraction problem, which another research group also recognized it in one of their works. So we tried to do something to develop a tool in which the teacher had to do less work. So just by automatizing the things, the processes that he has to do inside the classroom to collect and distribute learning material, and start programs and so on, just by a few clicks. So the dynamic of the presentation would be much better, much fluent, and well, it was in fact a good idea. We tried this in the University of Waseda. That's 2005. And if you see here the results, we had, we compared this environment with standard scenario, and in presentation, flexibility, absence of disruption, and follow-up, we got very good results. But not in preparation. Of course, it takes too much time to prepare. It takes time to tell the students what to do. And I was teaching with my software, just figure out what happens when another teacher uses that software. Okay? So lessons learned. HCI matters in learning scenario, and a lot. We have to minimize the interaction time. We discovered a lot of unexpected collaborative learning situations because of the synchronizing mechanism, which was object to object and not application to application. I could synchronize, for example, one of these programs with one student and another note with another student and so on. And we had a lot of very interesting collaboration situation inside the classroom, very rich. But it is good for a particular situation. So if you want to keep using computer technology to support your lecture, you have to move to another technology, to another application, and the students have to learn another way to interact, which would be not rewarding finally. And of course, setup time was too long. So we try another thing. We try what we call the deep board, which explored the gestures-based interaction. Very simple. Instead of dragging things and writing things, we just let the teacher make some gestures like an L, and the L will convert itself into a note where you can handwrite things. You can also double-click inside one of these notes and go inside, and again recursively. So that's what we call this deep board. And we saw that this gestures-based interaction was much better, much simpler. So lessons learned, keep it simple, okay? A simple learning material structure, simple HCI. To remember, we saw that pages are not the only simple way to structure learning material. 3D information graphs are easy to remember for the teacher. And this was used to support remote lectures between two campuses at the Waseda University in Japan, and is still being used, and not only by me. Contrary to the other application which is not used anymore, even by even by me, not used anymore. Okay, so I think well, we learned something. It was already 2005, and as I told you, we try to always use the technology to support learning. And the idea was to use mobile technology. And the first development was what we call the MC Sketcher. MC Sketcher to support collaborative learning scenarios in design. This was just taking a picture of somewhere and start trying to collaboratively design on the field by gestures. So this is how more or less would look like. That was a picture taken from a park, and then you can start sketching on it. The yellow spots are notes where you can go in and have more pages. So using this kind of mechanism, we expanded the screen somehow to the depth, not to the width, okay? So soon we realized there are many kinds of learning applications that use the same principle, and we developed framework which had two major components, one for gesture recognition and one to implement communications. Okay, so this was an API for developing peer-to-peer application easily, available in Java and C#. Why? Because we had a lot of very good applications already developed in Java, and we wanted this mobile world which worked better in C# to connect to these other applications. So we use this process of marshalling and marshalling for transmitting objects. So gestures are example of gestures are selecting with a double lace, or just clicking at what you have previously wrote, or making a dot. A dot here, and then everything what the line touches will be selected. Deleting is just a cross, and by selecting something you will see two dots, one red, one blue. The red is for resizing and the blue for rotating. The first example developing something with this platform was the MC Presenter, which supports configuring various working groups, creating on the fly problems and sending them to the students, and creating reshaping groups also on the fly by just gesturing. So this is more or less the system architecture. So the teacher configures and reconfigures groups, sends problems, and monitors the works of the student. So this is how the teacher would configure the groups. For each user, there will be an icon at the teacher's application, and she has to just drag the student's icon to the group. A group are created by just double clicking on the screen. So everything very swift. Problems, there are two kinds of problems: open problems and problems with options. Each part of the problem you could create by just handwriting, and also this L gesture which will create a note with all the content on it. And you can create then the notes for the question, the correct answer and the rest of the wrong options. And just by dragging them to the place where you want, you can have the quiz completed. Also there is a lot of collaboration between the students using this system. The students collaborate, for example, by trying to solve an open question by just handwriting collaboratively, or by having to select collaboratively and agree about the correct answer in an option question. So this is how the assessment mode will look like at the teacher computers. So the second example is in fact a set of examples based on what it's called participatory simulations. We didn't create this learning activity, we just implemented it. It's a participatory simulation. It's a role-playing activity in which, well, there are different roles and interaction rules, and students have to take a rule and interact, and they will, in doing so, they will learn something about the system which is being represented by this by this environment. So I have three examples, one in a trust building scenarios. The teacher created things to trade and two groups, sellers and buyers. So the students have to sell and buy things, and these things would have to could fail randomly, and the seller might opt in replacing it or not. Of course, if the seller replaces it, it will make a less profit, but it will gain the trust of the client. The second one is about a medical scenario. Here you have patients and doctors. Patients have symptoms and doctors have medicines, and the patients have to search for the doctor with the right medicine, and of course the doctor should give the medicine, and this trading is made by by proximity using the infrared device from the mobile computers. So if you get close to another application, you will have what we call the trading zone. You can drag things there, and they will appear in the trading zone of the other student. And the third scenario is the stock market scenario. I think you imagine what happens here. People sell and buy shares, and they see how the price might vary. So far, so good? Well, not quite, because we still have fragmentation of learning experience, different devices, different situation. If you want good the role-playing thing, good the design thing, and so on, but they are two different applications with two different HCI rules. So this is how I came to the LACCIR project proposal: integration of classroom activities, which are structured and formal, with the unstructured and possibly informal and unexpected activities outside the classroom. So the research questions are: can we implement meaningful learning activities with this model? Can we develop an integrated HCI across platforms? Can we or should we use widgets, gestures, both, and can we describe them with a pattern language? So the first example was about a pattern collector. So the teacher will explain a pattern, maybe an architectural pattern, to the students, and they have to go out and gather some data, taking photos, explaining this instantiation of the pattern, and go back to the classroom and show and share the results with the students. So this is the system functionality and some screenshots: creating patterns, instantiating patterns, linking patterns, which is very important in this pattern language, sharing patterns, and comparing patterns. So this takes place in the classroom, this outside, this can take place anywhere, then again in the classroom and anywhere. So this was the system architecture, and I'm running out of time, so I will not go into details. The last idea was to use also geo-collaboration because of the possibility to have GPS with these mobile devices, and we see a lot of learning scenario which may benefit from this geo-referencing of the learning material. So this is not ready, it's under construction, but look like this. So the teacher can prepare tasks. The tasks are collect patterns, maybe in following a certain path, which of course starts from our faculty. This is how to assign the students to the tasks. And this is how the students should view the tasks. So we also are engaged towards formally evaluating the gesture. This has turned to be not very easy because we have diverse platforms, and we have diverse gestures we can use. So what kind of evaluation are we searching for? This is not real data, but if you compare the red with the green, you will see, okay, the green is better. But if you compare the blue with the red, which is better? Which would you have? And this is just for one device. Then you have another dimension of many devices. So maybe we should search for something with a high mean value, but with less standard deviation or something like that. And this in three dimension. Okay? So where do we go from now? Even more devices, mobile and non-mobile, appear every day in the market, and we want to use them for supporting learning, but they differ. And the other thing, we stressed a lot this peer-to-peer platform. Is it really necessary nowadays when we are going to have internet even in South America, almost everywhere? So maybe we should try some some generic platform like HTML5, which has a lot of potential, and we could do the same thing just using HTML5. It runs still too slow. Okay, so I don't think if that today I mean May 2011 would be something that you can use in learning scenarios. The other one was modeling of TV signal propagation, which looks like this: the desktop environment and the mobile environment, also with activities inside and outside the classroom. So conclusions are: can we implement meaningful learning activities with this model? Yes, we can. Can we or should we use widgets, gestures, both? Yes. Only gesture is not good. You have to combine it. Can we develop an integrated interaction model across platforms? I think we can. It's not done yet. And can we describe them with a pattern language? We are working on it. Okay? So, thank you very much. That's my talk.
This question comes out from my complete ignorance on this field. And it's about the process of learning on a little child that is learning to read, for instance.
To what?
That is learning to read, for instance. And you're skipping the very process of writing itself just by dragging things. Am I clear or no?
Yes.
Yeah. So how is there any difficult or in the process of learning just by skipping this step of writing itself?
Only in that activity you can also write on this board. There is also handwriting, but recognizing handwriting is, and especially for children, is not not doable. So they have to first do it with this drag and drop, and then they have to write it by hand. Okay. So in this first step, of course, they don't have to write, but right after that, they have to write it.
They have to. Okay. Yeah. Thanks.
The original methodology was without computer, and the teacher had to read everything. Okay, so.
Yes. Thank you.
Thank you. So our
use the microphone. Good morning. My name is Álvaro Soto, and I will present the activities that we develop in our LACCIR grant. This is a joint work with Dr. Domingo Meri and Dr. Enrique Zucker. Great. Thank you. So it's from Catholic University of Chile and also from INAOE in Mexico. So first, let me state what is our challenge, what is our problem that we did in this LACCIR project. It was like try to count people waiting in lines, and we had two different environments. This one. One is this environment. In this case, is a convenience store, and as you can see here, in a convenience store, we usually have a view of the whole body of the people. And also in a grocery store, because in this case the people is using carts, you know, we only had a view of the upper part of the body, just the torso and the head. So this is the two scenarios that we face. So our solution is based in a combination of two techniques, one from computer vision and also the other one from machine learning. So probably you are not very familiar with some of the new techniques that are used in this computer vision with machine learning combination. So I will give you first some background information so you can understand what is our approach to the problem. So the classical approach for doing detection in computer vision is what is called template matching. So it's a very, very intuitive idea. You had a template with what you want to detect. Then you run this in the images, and then you fire a detection where the matching is high. So in this case, probably this will work very good. No, you have this template, and you will have these two detection. Unfortunately, this problem doesn't work pretty well in some unstructured conditions. For example, in this case, if you have some changes in the illumination, the value of the pixel in these images will be different to your template, and then you will miss probably the detections. Yeah. Also, if in this case the dogs, has a different pose of the head, again, the template will be different, and you will miss the detection, and also the scales. If the dogs here are in a close view, also you will probably miss the detection. So, template matching doesn't work pretty well in natural conditions. So another typical approach that people use in computer vision is what is called geometric model. In this case, you had a 3D model, a CAD model of what you want to detect, and then you try to do a match in different poses, in an image like this. So in this case, probably you are more robust to changes in the pose of the target, but also you have some problems. For example, intra-class variation. If you want to detect a different type of car, you need a different model. So, and you will have to have a specific model for any car. So this doesn't scale pretty well. No. Also, you have problem with occlusions. If some part of the target is occluded, you also have some problem with the matching. Deformation of background clutter are also problems that you can face for this technique. So also, it doesn't work pretty well in the general case. So in the last year, people in computer vision have been using some machine learning techniques to face this problem of detecting target or objects in images. So what is the approach of machine learning? Machine learning, you had a training set, so a set of images of how your target looks under different conditions, and then you had an algorithm that define a hypothesis space, that is mostly a model, and the hypothesis space is mostly the parameters of this model, and you had a task, and then what you do is you have some loss function, and you iterate the algorithms in order to find a good value for the parameters of the model so you can do the recognition. So that's mostly the machine learning approach. So for this approach, you need some training sets. That's one of the critical parts. So for example, in this case, for detecting faces, head in this case, you had like a training set like this. A lot of images of different people, different heads in different positions and under different conditions of illumination. So that's the typical training set. So in the case of the whole body, you need also for this approach some training set given by different poses of different people like this. Mm-hmm. Okay, so in using this approach, you are setting this problem of recognition as a binary classification problem. So in our approach, we get a lot of images from, in this case, the convenience store. From these images, we get the training set, a set of crops of humans, and also a set of crops of the background, part of the images that are not humans. So, and you set this as a binary classification problem. So one more background information is that in the representation, so the easy or more straightforward way is that you can use just the pixels in the images as your information. But it turns to be that the pixels are very not robust against some problems of the visual world, such as changes in illumination and so on. So usually people in computer vision use a different representation, what is called visual features. In this case, I show you one a visual feature that is called histogram of gradients. So in this case, you divide the images in a grid. For each cell in this grid, like this cell, for example, you calculate the histogram of the gradients, the different orientation of the contrast information, local contrast information in the images. So if you can see, you have here different, the same people, the same person, and the different condition of pose, and the histogram of gradient looks very similar, and it looks very different to another object. For example, a bike here, it produces a very different histogram of gradient. So this is a very discriminative feature. It's good for classification. So you have some good information, and it's invariant to some of the problem of changes in illumination and pose in this case, and it's because we are using some statistical information of the pixels. So a last point that I want to describe to you is that now when you get a new image, just in order to do the classification, you need to know in which part of the images is the candidate for a person or whatever you want. So the typical approach using computer vision is based on what is called image segmentation, where you try to detect some relevant parts of the images. But usually the segmentation, there is a lot of techniques for image segmentation, but they are usually not very robust. So what is now very common in computer vision is use this approach that is called a sliding window. So in a sliding window, what you are trying to do is mostly test all the possible segmentation, and you do but usually using some rectangular window, and you slide these over the whole images, so hoping that at some point one of these will get just in the position where you had your target, like this, and you will fire the detection. So this is a very intensive process, but you can do some saving. For example, in this case, you know that people are not flying here, so you just focus this sliding window, and you try this at different scale, because people can appear in the images at different sizes. So believe me, you can run this in real time. Your computer today are able to do this in real time. So okay, now everything is set to tell you about our approach to this detection of human. So we get the training set, images from people, images for background, and then we set, using the detection of our goal, that is detecting people, and the sliding window process, we set the parameters of one of the classifier in order to do the detection based on those training sets. So that's what we are doing. Okay, then our first contribution in the work that we did in the LACCIR grant was to develop some new visual features in the part of the representation. And in this case, we did some a study in trying to detect some features that are similar to some biological process that usually happens in the human brain. And these are cells that detect some difference between the center and the surround. For example, you have cells in the brain that detect difference when the center is bright and the surround is dark, and the opposite. So we approximate this with a rectangular shape, and we try to do this. And using this, what you get is some map of what is salient in an image. So for example, this is an image of Cartagena, and when you apply this feature, you can see that you have some salient part, like these towers, for example, and that is very good because it gives you some information about what part of the images are very interesting for doing detection. So people before used this technique of saliency too. There's a work by Edie in 98 and a work by Fintrop in 2007. And this is the result of our approach. As you can see, the most important difference between these three is that the resolution of our saliency map is better than this and also than this one. And the reason that is better is that these people, in order to run cells of different sizes, so they run this center surrounds analysis by downsampling the images. And by downsampling the images, you're mostly losing resolution. And they do this because processing efficiency. So in our approach, we use what is called the integral images. And the integral images is that an image where each pixel is the sum of all the pixels in the previous columns and rows. So you need to, for doing this process, you need to first apply these integral images. And the good thing is that when you have that images, then any center surround size filter that you want to apply on the images, you can just do in the calculation using sums in between 2 pixels. No? So in terms of being the computation complexity proportional to the size of the center surround filter that you are doing, is just proportional to 2 sums. No? And the only catch is that you need the overhead to calculate first the integral images. But it turns to be that you can be able to run this in real time very, very efficiently. So if you try this in humans, you will see that this is the typical saliency for humans, and this is for other objects. And you can see, mostly the shape, the silhouette, that is very informative about the humans when you run the saliency in humans. So we test this in some human detection, and we get some good results. And the second approach that we did for visual features was in terms of using a fixed pattern to detect visual feature. We use machine learning to detect which pattern are more discriminative for doing the classification. So in this case, we modify a very popular visual feature that is called local binary patterns. So a local binary pattern is, it works this way. You get a small patch from the images, and you compare the center pixel of the patch against the neighbors. No? So in the neighbors, it has a lower value, you put a 0. If the neighbor has a bigger value, you put a 1. No? So when you do this, you get like a pattern of binary numbers, and that is the local binary pattern. So in this case, for this feature, this neighborhood is fixed. No. So in our work, what we did is that we use a decision tree, a machine learning technique, to we search. Our hypothesis space was like a neighborhood of 7 by 7 pixels, and we tried to see in that neighborhood what are the better pairs of pixels that are more discriminative to do the classification. So we train a decision trees, getting neighborhoods and pixeling a 7 by 7 pixels in a 7 by 7 neighborhood, and we run a decision tree and we get rules like this. For example, if the center pixel is less than some of the pixels in the neighborhood, and this and this and this, so you get good classification. So we use this rule as our local binary pattern. So in this case, the local binary pattern are not fixed, but are given by the output of the training of the decision tree. So it's a simple idea, and we test this in an application for face recognition. And this is a benchmark in a standard face recognition application. These are other visual features that are very popular in the face recognition community. And this is our approach, and we get very good numbers for the face recognition using this visual feature. So that was our second contribution in this LACCIR grant. And then we had like the people detection. And for the people detection, then we use a very large band of different visual features. We use this histogram gradient that I mentioned before, local binary pattern, our local binary pattern based on decision trees, and saliency application of all this in the saliency map that I also described before. So if you try all these features in an image, you have a very high dimensional vector. No? You get around 20,000 dimensions if you run all these features in an image. So that's very difficult for any machine learning application. So we apply some dimensionality reduction using what is called partial least square analysis. That is very similar to principal component analysis, but it's more discriminative. It's more like feature discriminant analysis. And using that, we reduce the dimensionality for these 20,000 dimensions to around 20 to 30 dimensions. So as a classifier, so this is our representation. Yeah. The classifier was a regular support vector machine. We use a radial basic function kernel. For the sliding window, this scanning, finding target, we use an 8 pixels displacement. We move 8 pixels for the next window, and then we slide over the whole images. We use 8 different sizes for these windows, that is the scale, and we use also normal signal suppression of 0.5. When you do this sliding window, when one of the windows, the classifier for one of the position of the window fires, probably the window that is close, 8 pixels in the side, will also have some information about the people that will also fire. So we just consider there the overlapping. If the overlapping of the windows that fires are more than 0.5, we just consider one detection. So that's the maximum suppression. Okay, so we test this in a standard benchmark dataset. This is the INRIA dataset. This is standard benchmark for people detection. As you see here, this is common images, not structured, very natural images. And we use as training from this dataset around 2,500 training set for positive example of humans and 1,200 for background. And we bootstrap 5 times. What is this bootstrapping? Is that you get this training set, you apply this to the machine learning, the support vector machine, you get the results, and then you run this classifier in images with no people. So you get all the detection there that are false positive, and then you enrich your training set and you train again. So in some sense, you are improving your training set with more difficult cases, and at the end you get a better classifier. So that we repeat this process 5 times, and then we test in this data. So this is our result. This is the typical way that you show the result in this detection. In this axis, you have the accuracy. This is the miss rate. So for example, this means that you are around 92% accuracy. And this is the number of false detection for window, for detection for window. So when you get 1 million windows, you probably get here around 92% accuracy and 1 false positive for million windows. So that's mostly. These are another approaches that are state-of-the-art in this area, and we get very good results, as you can see in this curve. So this is some of the results, So here, for example, you had a bug detection. There's kind of a phantom people there, detected by this system. And here also is very interesting. These algorithms are still a little bit dumb. You believe that here is a people, probably because the shoe here is like a head for the algorithms and find a bad detection. So we test also this. There's a company in Chile that is providing this service to some convenience chains. They are doing this manually now. They're daily giving a report to what was the length of the queues in these stores, and there are human people doing the counting. So we are doing this now with a combination of this system and humans. A human is kind of checking how was the counting. It's doing the counting by itself. So these are images of these cases. So for example, here we had a problem. This guy here, because the position of the camera is not probably the best one, low occlusion, and we are missing that count. We're counting this, but not this one. So, well, this is the result. We're getting around, with this method, around precision, the 90%, a recall of around 80%. And these are the cases where we are missing. For example, here, because there is occlusion. And here we are missing this human because the position is not really good in terms of what we provide to the algorithms in the training set. So we had an improved version of the system that is, in terms of detecting the whole body, we are detecting just parts of the body. So in this case, what is a relevant part, where they are located is kind of one of the challenges, and we use an unsupervised learning approach for this. So the idea here is that we try to detect relevant local part of the images. So what is relevant? For that, we use the output of the support vector machine, of a linear support vector machine, and in that case, these are the weight, of the support vector that are defining the model. And where the weight are had a larger value, so it means that part of the images are more relevant. So we are using that, detecting this relevant part, and then we are trying to classify it just based on these local parts. I will give you an example. Here are one of the classifiers that appear with this method. So this classifier is mostly based on legs that are closed. So this is another classifier that appears with another set of examples that we use for that. And this is another classifier that is probably detecting legs, but where they are open. So that is how we define parts. And we run classifier then for any of these relevant parts. That's mostly the approach. And this is the result that we get. So in this case, we are not detecting the whole body. So we're running a bank of different classifiers, and each of the classifier is specialized in different parts. So, for example, some of the head, frontal head view, legs, and so on. And with this, we are now getting results around 90% accuracy for the detection of people. Okay, so finally I will give you some information about some of the approaches that we are doing now. This is an application where we are trying to count the number of people in a classroom. So like here, for example, you know. How we are doing this, we are setting 4 cameras in the 4 corners of the classroom, so we're getting them 4 images. When we have more than 1 image, in the case 4 images, we can do a 3D reconstruction. We can have 3D information of the environment. So in this case, we are selecting this yellow area, that is the area that all the camera has an overlap to do the detection. Yeah? And we are detecting the faces. So I had a video that I can show you about this. So first we define the space of interest. This is the cube. So because now we have 2D information in terms of doing a sliding window, we are doing a sliding cube. And we are trying to detect heads. No? Because when the people is seated, we don't have a view of the whole body, just the upper part. So that's the, in this case, not a sliding window, but a sliding cube that is moving around the whole area that we define relevant and trying to detect, in this case, the head of this. So these are some of the results that we get with this. Now, when you do all these cube sliding, you know, you get like the detection of the heads, and that's mostly, you know, the result that you can see here. Well, we're also mounting this in our robot to do some human-computer interaction, and we're kind of continuing this application to detecting people. So this is part of the work in our research group in machine intelligence in Catholic University. These are some of the mates in this group, and that's it. Thank you.
Thank you. So let's have one question. No? Maybe I will ask.
Okay, go ahead.
When do you think it's possible to count number of attendees in this room?
Oh, actually, we're getting very good results, and we're moving to a second phase that, I mean, I can show you a video, because one of the things is that you can count people, so that has been very good, but now we're trying to recognize the people that are in the room. So in this case, I can show you the video here. Yep. Okay, yeah. So with the overview camera, it's very difficult to have the resolution to identify people. So what we are doing is that trying to detect the head. You know, like this. This is the setup of my student, huh? And he's trying to get a zoom of the face. So with that images, we can also do the recognition of the face recognition. So as you can see there, it's detecting another face, and then getting the zoom to get the recognition. So you can, at the beginning of the semester, you can register the faces of all the people that attend a class, and then you can take the assistant of the class, you know, with an automatic system like this. You know, that's what we are trying to do in that context. So taking just the number of people in the classroom, but also try to identify who is the people in the classroom.
Great, thank you.